All right, we're recording. Plan B seemed to work. Plan B worked. All right, nice. Okay, so today we're going to look at applications of angles. So we know what an angle is. An angle is a measure of what? No, that's a trig function. That was Mr. Pierce for the record. He was answering, though. He was volunteering. No, an angle measures what? Length? Temperature? No, it measures rotation. Good. An angle measures rotation. And we can measure it in degrees or radians. Right. And, of course, there's degrees and degrees, minutes, seconds, decimal degrees and degrees, minutes, seconds. So today we're going to look at applications of angles, which basically is going to look at anything that involves circular objects or like the physics examples y'all had earlier in the year, anything that rotates. Anything that rotates is going to exhibit some type of angular velocity, which will be how fast it rotates, angular acceleration, angular momentum, I think y'all studied as well. Torque would be another one that involves rotation. Most of y'all drive an automobile and you'll have a tachometer in the car. You know what the tach measures? The tachometer. It's the one next to, if you have it, it's next to the speedometer. Yeah, RPMs. Yeah, it measures how fast your engine is spinning in RPMs, which stands for what? Rotations per minute or revolutions per minute. So that is a type of angular velocity. It measures how fast your engine is rotating. So we're going to be looking at that in this section. But the first thing that we're going to do is we're going to take the definition of a radian, measure of an angle, and we're going to modify it. So from 5.1, who remembers how to define the radian measure of an angle? Theta. Ah, very good. It's the arc length, which we call S, divided by the radius R. Why do we use S to represent a length or a distance? Wouldn't D be a better choice? We use D sometimes. Where do we get the Z for the integers? The German verb to count. So guess where S comes from also? It actually comes not from Latin, but from German. Strecke. Strecke. What is Strecke in German? Tate. Anyone else take German in here? I know you did. We speak German every day at home. It's German for distance. If you had to guess, that would be a good guess, and you'd be right. Strecke. So I know in physics you use like S of t for a position equation, and that's why. Y'all don't? It's pretty customary to use S of t, B of t, and A of t. Okay. All right. Well, we're going to use S in this class to denote the distance or the length, the Strecke, around a circle, around the circumference of the circle. And we might measure that in like feet or miles or any unit of length divided by the radius, which we would also measure in units of feet, miles, or whatever length it is. And therefore, what happens with the units when we have the ratio here? S divided by R? They go away. They divide out, and we end up with theta is a unitless measure of rotation, okay? Which is why we use radians when we have applications that involve length or distances. So we can assign the x-axis to be anything we want, not just degrees. All right, if I take that equation and I just simply multiply both sides by r, I get S equals r theta, which gives us now a handy-dandy formula for finding the arc lengths of something that does not complete a full rotation, because that would be the circumference. R is the radius of the circle, and theta is going to be the angle of rotation in what units? Yeah, well, not in radians aren't units, but it has to be in radians because it's unitless. Okay, because we'd have the arc length measured in feet. The radius, let's say, would be also measured in feet. Feet times degrees is called feet degrees, and that's not a unit of length, right? But feet times radians is, guess what? Feet, because what are the units of radians? There are none. All right, so let's look at a quick application. This is not our city, but I wish it were. Find the distance that a runner travels in miles if he runs along a circular track that has a radius of 5 miles. That'd be cool to have a city with this outer track that runs around the perimeter of the city that's circular. You know, it'd be a nice, safe place to kind of rollerblade if you're in the 90s. or bike or jog, whatever. But we don't have one. But this city has one, and this guy is taking advantage of it. So 10-mile radius, 10-mile diameter, sorry. Small, right? It's relative. I don't want it any bigger, like small town. What's the diameter of New Braunfels? I don't know. 10 miles would be, that's a big city. Well, whatever. It's not like, never mind. He's running around a track that has a 5-mile radius, okay? But here's the thing. He doesn't even complete a lap, loser. He's only running through an angle of 300 degrees. He can't even make a complete lap around the circle, right? Now, before you laugh at him for not being able to make a complete lap, your job is to figure out how far did he actually run in miles, okay? I'm going to let you try it. Here's a hint. S equals R theta. Go. You got it? Already? What'd you get? Sehr gut. Sehr gut. Muy, muy bien, bien. I believe you do, yes, sir. He's not such a loser, right? That's still kind of a long way. Yeah. I'm not going to laugh at him. I think you got the wrong reference angle. Yeah, 7 pi 4 would be 315. Oh, nice animals. Are they on the track? Which one to jog with your animals? Those guys look short-legged, though. They don't look like they could make it with them. Yeah, like a little chihuahua running around that track. Remember, pi over 180 is a better conversion factor because it's simplified. You did 2 pi over 360, but that's the right answer. Okay, most of y'all have the right answer. That's good. Let's go ahead and plug in. If we're trying to figure out how far he's running, which variable are we interested in finding, S, R, or theta? S. That would be the distance around the circumference, okay? So the radius of the circle is 5. I'm going to go ahead and put my units in there for now, miles, and he runs through an angle of 300 degrees. Now, a few people I noticed actually multiplied those together and got 1,500. But look what the units would be. Miles, degrees. So there's bragging and then there's really bragging. So if you went up to your friend and said, man, I ran 1,500 miles degrees, they're going to be like, no way! I don't even know what that means. That is crazy. Because the units don't make sense, do they? We don't measure distance in miles, degrees. So you're going to have to be looking for some new friends if you go around bragging about that. So what's the problem here? 300 degrees is not what we want. We have to convert it to radians. Okay. Now there's a couple ways to do that. You could do that off to the side as bench work, or you can convert it right in here by multiplying by pi over 180 so that your degrees divide out, or 2 pi over 360, whatever. That's the simplified version. Yes, that's the other way to do it. The other way to do it is just to realize that 300 degrees is on the unit circle, and it's our pi thirds reference angle, so it would be 5 pi thirds. Rads. So however you want to do it, your angle's not always going to be recognizable from the unit circle. So this would be in general how you do it. And you can convert it in the problem as a stoichiometric conversion, or you can do it off to the side and then bring it back into the problem. But what would be the units now? What are miles times radians? Miles. And is that reasonable for a distance? Yes. Now, do we want to leave pi visible in our answer here or multiply it into the answer? Yeah, we want to multiply it in. The only time we really want to leave pi visible is if it's an angle in radians that's a nice ratio. Otherwise, we'll multiply it in. So now we go to the calculator, and we'll type it in 5 times 5 times pi, use the pi button, and then divide it by 3. And then you report 3 decimals. So 26.179 miles. So I am definitely not going to make fun of this guy for not making it all the way around once. Because he ran just short of a full what? Marathon, which is 26.2 miles. Yeah, 26.2. The extra 700 or so yards after the 26 miles were in some Olympics to accommodate some king who wanted to sit out on his balcony of his castle and watch the marathoners finish right in front. So he had them extend the finish line another, 700 yards or so, which is the 0.2 of a mile, so that he could sit there and watch them finish. And then it stuck. Once they did it that way, they're like, well, now it has to stick so that we can compare apples to apples in future Olympics. Yeah. Yeah, it actually happened. Because what was the original length of a marathon? 26, because that was the distance that, what's-his-face, the Greek runner, the messenger? And then he died. What was it, Phidippides or something like that? He ran 2 marathons to deliver a message, and he was like, 26 is more distance than any one person should have to run. It's impossible. And then he died. Okay, and now people are in 26 miles without dying, but they're still crazy. Okay? They're still crazy. Now, you have crazy people, and then you got crazy people. They're ultramarathoners. And they run distances that exceed 26. They run 100 miles, 150, 250, whatever, and they run through extreme conditions. Like there's a California race that runs from the top of Mount Whitney to the bottom of Death Valley in one race. It's over 100 miles. You go through one pair of sneakers on a race like that. Yeah. No, you run the whole time. You run the whole time. It's called ultramarathon. Then you probably don't because you're sweating out a lot of stuff, right? Yeah, and you're not eating a lot of stuff along the way, like a plate of enchiladas, you know. They run like 30 hours. Yeah. Yeah. Yeah, I know. It's crazy. Yeah. So anyway, let's look at example 2. We got the runner from example 1. Y'all remember that guy? Okay. He's now running along the exact same track. You remember the track? But now he's running an ultramarathon of 150 miles. We want to know now through how many degrees did he run? And that's not like outdoor temperature degrees. We want to know rotationally through how many degrees did he run. On your mark, get set, go. Did you already finish that one? I'm going way too slowly for you GT kids. Because nothing else was on TV. And so you watched the video last night. We missed you too. Yeah. S equals R theta. This time 150 miles is which variable? S, Did the track change sizes or the same track? Same, so R is still 5, and now we're trying to find theta. Now, what are we measuring 150 and 5 in? What units? They're both miles. Good. So when we divide through, we get 150 divided by 5, and that's the definition of a radian. The miles divide out, so we end up with 30. But not 30 degrees. That's unreasonable, right? That's 30 radians. So let's go ahead and see how many rotations is that about? One rotation is about how many radians? 2 pi, which would be about 6-ish, right? So that would be probably a little bit less than 5 laps. Okay? But if I want to convert that to degrees, I need to multiply by who over what? 180 degrees, good. The units we want to appear in the numerator over pi rads, the units we want to divide out in the denominator. And someone help me out here. 30 times 180 divided by pi with the calculator. Ms. Martin, I know you have it. Good. Very good. That's a lot of degrees. So if you have that guy now, he's going and bragging again. He's telling, yeah, man, I ran through 1,718 degrees. One of his dumb friends said, man, that's hot. How'd you not melt? And you're like, no, dude, no. No, were you not listening? Do you know anything about math? Come on, man. Like, no. And you get new friends. Okay. So anyway, is it almost 5 laps? Yeah. 4.774 laps. Okay. So that would be a cool city to have a 5-mile circular track around its perimeter, because then you can host marathons, right? And it would be, you can call the marathons like not even a full lap marathon, right? That'd be a great name for it. Right, the last little piece is food, right. Now, it is interesting. I've run a couple of marathons, and right at the end of the marathon, there's people with signs that say, free beer that way, to try and tempt the people who are on the last, whatever, mile. The last mile or two are hard. And there's people with signs, free beer, free finishing, or like knockoff finishing shirts, $5, because really most people run just for the shirt. But you can oh man, it's tough. I can go over here and pay $5 and get a shirt that's almost identical to the other one. Yeah. So there's a lot of people that try to tempt the runners at the end. So maybe this guy was tempted by something. Maybe he saw a cute little puppy dog, and he got off the track, and he didn't quite finish the marathon. But anyway, let's look at example 3. It says to derive the formula for the area of a sector of a circle with a radius r and a central angle of theta. Now, the first thing we have to do is figure out what the heck is the sector of a circle. That sounds like a government building, right? Or a place inside of a government building. Sector 5, top secret. No. Okay, so let's think about pizza. Have y'all ever heard of pizza? You have heard of pizza. Now, unless it's Totino's frozen pizza, most pizzas are circular. Totino's now is rectangular, right? You get the same square footage of pizza, but less packaging. I applaud them for that. But it takes it's round at least, right? So most pizzas are round. If you eat a slice of pizza, and I'm talking about a pizza that is meticulously sliced, not the kind of pizza where they just do it in a hurry, like, round, and you get the pizza that's sliced not even through the center, and you have like this big slice here and that little slice right there, That's like crazy slice. Wow. We're talking about a pizza that is meticulously sliced so that it's sliced perfectly through the center of the circle. Then a slice of pizza is what we call the sector of a circle. Okay? And so we have a radius on either side, which kind of now makes it resemble an isosceles triangle. The only difference, instead of being flat along the bottom, you have the crust, right? Could be stuffed or not. We call that the what? We call that the arc length. Yeah, which is r theta. The angle then, theta, is the central angle. So what I want to do now is I want to figure out, I want y'all to derive, because I don't think there is one in existence just yet, derive the formula that will allow me to find the area of a slice of pizza just by knowing the radius of the pizza and the central angle of the slice. Derive it. How do we derive something? We have to start from scratch, don't we? Or build upon something that's already there. Yeah, it looks like it's a geometry thing. How do we derive? Those are pretty simple instructions, but man, they're loaded, aren't they? Derive. It's like invent humanity. Oh, man. That's hard. A proportion. There you go. You can build off something that we know. What do we know about a circle? If we're trying to find the area of a part of a circle, do we know what the area of an entire circle is? What's the formula? Pi r squared. So you can use the mathematical tool of proportions to help you establish this, right? And typically for proportion, we go the part is to the whole, and that's W whole, not H whole. as the part is to the whole. Part is to whole as part is to whole. So because I'm looking for the area of the sector, let's let capital A be the area of the sector or the pizza slice that we're looking for. So on the left side here, I'll say that A, the area of the piece or the part of the circle, is to the area of the whole circle, which is what? Pi r squared. And now I need to come up with two other things. Part to whole, part to whole. What can we do? What can we do? S, good. The part of the circumference, which is r theta, right? The arc length, is to the arc length of the whole circle, which we call the what? Circumference. And what's the formula for circumference? 2 pi r, okay? Thanks, Archimedes. We should do it together on the count of 3. 1, 2, 3. Thanks, Archimedes. Yeah, he gave us these two equations down here, pi r squared and 2 pi r. He's also on the back of the Math Club shirt this year, which they look great, by the way. Okay, so there you go. Part is to whole is part is to whole. So what variable are we trying to solve for now? A. What happens over here on this side? The r's divide out. Which means you could have, instead of doing part of the distance to the whole distance, you could have done central angle is part of the rotation to the entire rotation, which is how many radians? 2 pi. So theta is in what? Degrees or radians? It's in radians, right? So the radian measure of the central angle to the entire radian measure of a full rotation, which is 2 pi. You could have done that as well. All right, so now I'll multiply both sides by pi r squared, and I get pi r squared. Totinos are actually rectangular. Theta all over 2 pi. And we have a formula now for the area of a sector. But is that a pretty formula? Don't hurt its feelings, but it could look better. What happens with the pi's? They do what? Divide out. Good. And all we're left with in the denominator is 2. So dividing by 2 is the same as multiplying by what? 1/2. So we have 1/2 times r squared times theta, where theta is in radians and r is the radius. Good. Congratulations, guys. You just discovered a new formula, the formula for the area of a sector. You should publish your results and get famous. All right? And since you derived it, since you invented it, you probably already remember it, right? You know it by heart because it's your baby. So without looking, what's the formula for the area of a sector of a circle? Good. 1/2 r squared theta. You think I'll give that to you on a quiz or a test? Say no. No, I will not. You have to know it. Okay? But you don't forget your baby's name, do you? Oh, that's us.
At this time, would you please release the students that have a blue pass to the auditorium for a short meeting? If the student does not have their pass, there is a list of students on email sent out by Ms. Burton. So you can check that list. Those students need to go to the auditorium at this time.
We're going to keep going. I'm just going to record it. We're going to be doing the Freudian pizza example for Mr. Kilford. Sorry y'all are missing it. All right, I'll post it in there. All right, so to summarize here, the definition for the area of a sector of a circle is A equals 1/2 r squared theta. So I guess it wasn't novel. Y'all, it's right here in print already, so I guess it existed before the second period today. Okay, well, it was worth the shot. All right, so let's try it out. Example 4. Mr. Kilford, y'all know who that is. Downstairs, psychology teacher. If you never had him as a teacher, you should probably sign up next year to have him. Wonderful teacher. He and I are pretty close friends, so he helps me out. He likes pizza, and he knows I like math, so it works out great. Okay, that's fine. Yeah. Okay, thank you. So Mr. Kilford just wolfed down a slice of Freudian pizza. That's a pizza that is named after Sigmund Freud. That had a 40-degree central angle. I know you're thinking, how do we know it had a 40-degree central angle? He always measures the slice angle for me because he knows I care, and he knows that I also use them sometimes in problems. So that's pretty accurate. He has a little device for measuring it. Ask him to see it sometime. If the slice came from a 14-inch diameter Freudian pizza, and if you go over here to the New York Pizza Pub and you order the Guilford Special, it'll be a 14-inch Freudian pizza. Okay? Kid you not. Try it out sometime. We want to find the perimeter of the slice that Guilford ate. Now here's an actual photograph of a slice of Freudian pizza, drawn to scale. It's actual size. Okay? Scaled down. Actual size scaled down. Or scaled up. So, it kind of looks like a cartoon, but that's a photograph. That's just how Freudian pizza looks. It also has little slices of Sigmund Freud on it as well, like pepperoni slices, but they're slices of Sigmund Freud. And you can see he's got little marinara on his face and beard. Okay. So we want to find the perimeter of this slice. So that would be essentially if we were to walk around the slice of pizza, how far did we walk? So let's start at this corner. If I walk from here to here, how far did I walk? And this is, by the way, a pizza that is meticulously sliced through the center. So if the pizza was a 14-inch diameter, what is that? That's 7 inches. Yeah. And then I walk back up this corner, and that should be another 7 inches. And then I walk around the circumference part of it, which we call the arc length, which should be r theta, right? We'll call that S for now, which is r theta. So let's come over here and write an equation then for the perimeter. Call it part A. I'll use P for perimeter. In general, it's the radius plus the r theta, which is the arc length, yes? So you can simplify that and call that 2r plus r theta. And if you want to factor out an r, you actually can. I'll leave it, though. So let's go ahead and plug in. 2 is 2. The radius of the pizza is 7 inches. I'm going to put inches there. Plus the radius again is 7 inches. Times theta is the central angle, which is what he measured to be 40 degrees. Another one.
I got 3 this time.
Let's see if they're here. They might be in the assembly.
Jason Wheat.
He's at the assembly.
Bridget Martin.
She's at the assembly. Yeah.
Jacqueline. I don't know how to say this last name.
Aside, she's here. Jackie's here. Yeah.
Not in trouble yet.
No, she'll be back soon. Okay. Yeah, we are towards the end. All right, so if I added these together, are the units going to match? We have inches plus inches degrees. That doesn't work. So what do we have to do with the 40? We have to convert it to radians. Yeah, and you can do it right there in the problem by multiplying by 180. No, 180 over pi, is that right? Would that work? Pi over 180, good. If you look at the units there, that's degrees squared over radians. We don't want that. So the units to divide out have to be in the bottom. Stoichiometry tells us what to do, and that should work. So now, if we just type that in, and I don't even think I need to show y'all on my calculator. I'll do it with the handheld. It's faster. Y'all can do the same. That's 14 plus 7 times 40 times pi. Use the pi button, and then divided by 180. And we report how many decimals? 3. So I got 18.886 inches. So that's the perimeter of the slice of pizza. But now, the bragging rights comes from telling someone how much square footage of pizza they ate. So that's measuring the amount of pizza you ate, not by the slices, or when you're eating your pizza with your math nerds, by the number of sectors of pizza slices that you ate, but instead by the square footage. Man, I ate some tons of pizza. Now, here's a little hint that might be helpful. Someone whose actual foot is actually 1 foot long has a foot that is actually 1/5280th of a mile long. Did you know that? It's a factoid. Maybe that'll help us. Maybe not. Now, the first thing that you're going to realize is that if we're trying to measure area in square footage, we're measuring length right now in inches. So we're going to have to do some kind of conversion factor. But first things first. If we want to figure out the area of the sector of the slice, we need a formula for the area of the sector of a circle. What is it? Without looking. 1/2 r squared theta. Good. So if A is what we're looking for, what's the value of 1/2? 1/2. Good. We know that. Sweet. What's the value of R? 7. Now I'm going to leave it as inches here because there's a couple ways to do this. And theta has to be in radians. So you could do the conversion again Well, let's go ahead and do this in our head. If you simplify 40/180th, the zeros divide out, so you're left with 4/18, which simplifies to 2/9, right? So that'll be 2 pi ninths. So the measure of the central angle is 2 pi ninths radians. And I won't even put rads there. So we have inches squared times radians, which is what units? Inches squared. And that's reasonable for area. So now if you type this into your calculator, that's going to be 49 divided by 2 times 2 pi divided by 9. I get 17.104 square inches. Now, if this were a test question, guess what one of the answer choices on the multiple choice would be for a question just like this? That, 17.104. I would probably already also have the answer in there where the person just multiplies by 40 instead of 2 pi ninths. But that is a correct answer, but it's not answering the question that was asked, right? We want it in square feet, and that's square inches. So if you're going to convert it after the fact using stoichiometry, you need to get rid of inches twice. So I need to get rid of inches and introduce feet. So what would be the conversion factor? How many feet and how many inches? 1 foot is 12 inches. Now, if I do that once, that gets rid of one of the factors of inches. I'm going to have to do it again. And now I have inches squared divided by inches, which is 1. And on the top, I'm left with feet times feet, which is square feet. So that's one way to do it. The other way to do it, so you wouldn't have to have two conversion factors, is if you would convert 7 inches first inside the squared. 7 inches, if you multiply by the same thing, 1 foot over 12, 7 inches is 7/12 of a foot. So it could have just been 7/12 quantity squared, which would have been 49 1/44. But we're still going to get the 144 out of it here. So now if you take the exact answer, which should still be sitting in your calculator, and you divide it by 12, and then divide it by 12 again, or divide by 144 twice, you get this answer here. You get it equals 0.118 square feet. And that's a lot of Freudian pizza. 118,000 square feet of pizza. It's hard to eat more than one slice, so there's always leftovers. All right. So an interesting question, but it deals with arc length, kind of in a novel way, perimeter. Deals with area of a sector in a novel way, pizza. You don't usually think of that. And we'll stop right there because everyone else is gone. All right, so tomorrow we'll pick up with directional applications, and then we'll look at, well, no, tomorrow we're not going to do that. Tomorrow we're going to take our little unit circle quiz in 4 minutes, and then we're going to go outside and do the little activity, which involves angular velocity.